Dear friends, welcome to this electrical engineering knowledge sharing channel AMP Power System. We are discussing workshop 5. We have already completed 4 sessions. Now we are going to discuss another new session, that is session 5, where we will be discussing transformer sizing for combined load. That is, combined load means there is a base load or continuous load, along with there is a big size motor which is approximately 25 to 50% of the base load. For such a installation, if we need a transformer, how to size the transformer. So that type of transformer sizing we will be discussing in this session. Now, to decide the transformer size means kVA of the transformer along with the voltage drop calculation, if we want to do such a combination of loads. So we have here again we have the 3 steps. Number 1 step, we have to find out that how much continuous load is there, which will be always over the transformer, along with for the motor how much running load is there, as well as how much starting load is there. So this starting load and the running load of the motor to be evaluated separately. Then we will be add up that load with this phase load or continuous load along with some spare capacity. And from that figure we have to optimize which size will be most appropriate to run the motors successfully, including starting. Once the transformer kVA is decided, then we have to calculate the voltage drop using percentage impedance, from which we can conclude the transformer sizing. So let us consider a installation where we have I will be using a numerical or common with a normal common general approach. Once we general approach is over, then we use a specific numerical example to clarify it. For general approach, what then in that case, what we have a 2 type of load. One is a base load or continuous load. We can say base load. So this base load has a 3 part. One part is a kilowatt part, another is a kVAR part, along with a power factor. And we can calculate kVA from here. So first base load part, if we calculate for all the loads, we have this figure. First for the base load, suppose we have a base load of P1B is the base load, okay, kilowatt part of the active part of the base load, and then we have a kVAR part P1. This is a Q. It is not P. It is suppose Q. We will use kilowatt by using P. kVAR will be using Q, and kVA will be using S. Q1 base, and power factor, suppose power factor F is F1B base power factor. And if once we need the kilowatt base power factor, if we divide kilowatt by this, we will get the kVA. So we can write down S1B is the base kVA. This is the continuous power part, okay, continuous or base power, okay. This is we decide first. Second, for the motors, we know the motor kilowatt. So motor, we will be telling motor running kilowatt, okay. So motor running RM, motor running kilowatt. Q you will be using for motor running kVAR, and F1M, F1 RM motor running power factor, and then motor running kVA. This is, we can calculate this. Then third we will calculate motor starting kilowatt, then motor starting kVAR, motor starting power factor, and then motor starting kVA. That means apparent power. Once we decide this thing, then from this we can calculate how much normal running condition of the motor, how much kilowatt. So if we consider motor running, total system running, when the motor is normally running along with the base load, then how much running kilowatt is there. If we say P running, that is running kilowatt of the system equal to PR, that equal how much? That is a base load running plus motor running, that is a P1B plus PRM. Both are in the same direction, because here we have, this is our, suppose this is a kilowatt and this is a kVAR. So this direction we are adding all these parameters, then finally we will calculate the kVA. So this is for the running condition, this is for the base load running kilowatt, this is a motor running kilowatt. So this is, we get PR. Similarly, if we want to QR, running kVA how much? Running QR means base load base load, this is a Q1B, this part Q1B plus motor running Q RM, this is this, right? So these are two, we got it. Now from here, once we decide, then we can calculate S running equal to how much? A square root of this plus this means PR A square plus QR square. This will give the starting KVA. And if we want to know the running KVA, if we want to run the running power factor, F running, that equal to how much? That equal to, we can calculate the KVA. SR we know KVA. From here, you know, power factor equal to how much? Power factor is always kilowatt by KVA. So it is equal to P1, PR, we know PR and we know SR. So we can calculate power factor here, which is a combined load power factor. So this is for the running condition. This is the KVA required. We can calculate. Okay. Similarly, if we want to calculate the starting KVA requirement, that how we will calculate it? Now, during starting, how much active power required? SM. How much reactive required? QSM. So how much total starting power required? Kilowatt required. That is base kilowatt. P1B. That is a base kilowatt plus a starting kilowatt PSM. And how much starting KVA required? That is a Q1B plus this one QSM. We can calculate from here. Okay, then if we want to calculate the starting KVA, we can write down a starting KVA SS, that equal to how much? A square root of PS square plus QS square. So during starting, how much KVA required we can calculate. So this way, now here is a factor. Now when we will be calculating the starting KVA requirement with the base load, at that time the motor part, this part, if this is the requirement of during motor starting, if this is the active power requirement and this is the reactive power requirement, so this amount should come from the transformer. So the transformer which are going to size, that transformer should cater the base load kilowatt as well as this starting kilowatt of the motor. And similarly, QS, this is the base KVA and this is the starting part of the KVA. Now this also given by the transformer. Now we have said at the starting, this part, how much time it will flow? It is only 6 to 15 seconds, because motor starting time normally 6 to 15 seconds. So during that time, motor can be overloaded. So if the motor is overloaded by 150, we know this, if the motor running either 50% or 70% or 90% loading before motor starting, if the transformer is running with that load, we can overload the transformer by 150%. That means this starting kilowatt requirement for the motor and the reactive kilowatt of the motor, it can be catered by the transformer using its overload capacity. So this, if we consider 50% overload, that actually out of this PSM and QSM, how much to be catered by the transformer, that we can calculate very easily. Out of this PSM and QSM, whatever the PSM required, whatever the PSM required, this divided by 1.5 actually to be incorporated in the transformer. Suppose this is called P-SM. This amount of active power actually to be inbuilt in the transformer. If this amount of kilowatt inbuilt in the transformer, and with the 1.50% overloading of that inbuilt kilowatt, transformer can cater this amount of active power. Similarly, the Q-SM, which to be inbuilt with the transformer, this reactive KVA, that is equal to how much? That is equal to actually the amount required, QSM divided by 1.5. So this amount, whatever the actual starting KVA required, that divided by 1.5, that means 50%, considering 50% overload, that amount is Q-SM to be inbuilt in the transformer. That means actually during sizing of the transformer, we actually need how much? Active power required P1B plus PSM divided by 1.5, and here QSM also divided by 1.5, because during starting transformer can be overloaded by 50%. Considering that aspect, this factor will be divided by 1.5. So this will be P1B base kilowatt plus starting kilowatt divided by 1.5 will be the total starting kilowatt requirement, and reactive KVA requirement base KVA plus during starting, what is the kVA required divided by 1.5. From this we can calculate this your starting kVA requirement. Okay, so this way we can calculate, and once we decide, then we can calculate the voltage drop. Either there are two ways we can calculate the voltage drop. We said voltage drop we can calculate how? Voltage drop equal to starting kVA divided by short circuit kVA of the transformer. Voltage percentage voltage drop is equal to starting kVA during starting, how much voltage is starting kVA divided by short circuit kVA of the transformer. That is one way we can calculate. Another way we can calculate percentage voltage drop equal to transformer resistance into R cos theta plus X sin theta. Okay, this is if we into the starting current. If we calculate this will also give you the voltage drop. Either way we can calculate. If we know the resistance of the winding and the reactance of the winding, and if we know the power factor we know cos theta 0.4 for during motor starting, and then we can calculate this this way or by starting kVA if the with the percentage impedance. Either way you can calculate the voltage drop. So now let us calculate one typical example, then it will be more clear. Suppose now let us consider the numerical example where we have a base load of 2500 kilowatt and motor is a 1 megawatt motor running at 0.85 power factor. So if we consider the base load 2500 kilowatt, so this is a P1B 2500 kilowatt running at power factor 0.85 power factor. So the motor kVA, running kVA equal to how much? 2500 divided by 0.8, 2941. Motor reactive kVA how much? Motor running kVA into power factor, power sin phi of the power factor, sin theta point, if the power factor 0.85, cos theta 0.85, sin theta 0.52. So S1B into this. So these three parameters we can calculate. So then for the motors, how much we can calculate? Motor is a 1 megawatt motor. So motor running power is a 1000 kilowatt. Motor running power factor 0.85. Motor starting kVA equal to 1000, 0.85 means 1176. Motor kVA, running kVA equal to how much? We know kVA 1000, 0.85 is the kVA into 0.52. This is equal to 1.1176. Okay, this is this factor 1.76 into 0.52. This is coming to 612 is the running kVA. Now during starting of the motor, what will happen? We have said the motor will draw 400 times of starting current and power factor will be 400 times of starting current, means this will be 4 times of IR, and that has this current will be reduced by to 85% due to voltage drop to 85%. So when we will be starting the motor terminal voltage will be 0.85 V and the starting current will be 0.85 of 4I. If we use this thing, then motor starting kVA, motor starting power kilowatt will be how much? Motor starting kilowatt we can calculate PSM. This is equal to, if we calculate this 0.85, what we said, 0.85 into this into voltage into 0.85 into 4I. So these are the factor 0.85 into 0.85 into 4. If you 0.85 into 0.85, if you multiply, it is coming into 4, it is coming 2.89, and the power factor is 0.4, starting average power factor 0.4 if we consider, because motor power factor will vary from 0.2 to 0.6. If we take average, 6.2 plus 0.6, 0.8 divided by 2 means 0.4. So this is coming 2.8, 2.89 into 0.4, it is coming 1.16. So 1.16 into SRM, that is equal to running kVA. So we can calculate this motor SRM how much? This we have calculated. Motor SRM we have got, motor SRM equal to 11.176. You multiplied by 1.16. You will get during motor starting, the kilowatt is coming 1364. And motor similarly, motor QSM, motor reactive power is similarly, you can calculate this into 0.4 is the power factor, and here it will be coming sin phi. SRM into 2.89 into sin phi. Sin phi equal to how much? This is we have calculated. Sin phi is 0.92. If the power factor 0.4, sin phi will be 0.92. This is coming 2.65 SRM. 2.65 SRM. SRM is how much? We have calculated SRM is 1176. If you calculate, it is coming 3136. That is the motor starting kVA. You can see running kVA of the motor 612, but starting kVA is a 3136. And the motor kVA we can calculate during starting motor kVA how much? Motor kilowatt divided by power factor. If you do the power factor 0.4, 1364 by 0.4, you will get 3410. That is the kVA. Okay. Now we have to think another point over here. we have said that during starting the kilowatt and kVA, this amount of kilowatt is required and this 3136 kVAr is required. But 1364 kilowatt will be putting in the transformer capacity such that with the overload of 50% overload of the transformer, this amount of kilowatt will be catered for. That means the amount of kilowatt inbuilt in the transformer will be, this will be divided by 1.5 because 50% overloading will give this amount. So if we calculate the 50% overloading, actual kilowatt required in the transformer is divided by 1.5. This is giving 9.909. Only 909 kilowatt is required, additional kilowatt required to inbuild in the transformer. Similarly, reactive kVA, how this 3136, what is the reactive kVA required in the transformer, that will be how much is required inbuilt in the transformer. Again, it is divided by 1.5, so it is required 2090. That means when we are putting a transformer sizing, instead of 3136 a starting kVA requirement, we have to put 2090 a starting kVA requirement inside the transformer. So during running, what is happening? So during running, how much kilowatt is required? That is a base kilowatt plus motor kilowatt 3500. How much kVA required? 1529 plus motor running kVA 610 is 2140. That is for the running condition. So from this we can calculate the running kVA how much? 3.5 megawatt, that is square, and this is a 2140. 2140 means 215 we consider, that is square. If you calculate, is coming 12.25. 12.25 is a plus this one. If you calculate, this is coming 4150 or 415 MVA. Okay, that is the running kVA required of the to run the load. We need 415 MVA total power. Okay, to run the load. And now with this we have to consider as a 20%, as it is as a continuous load 2.5 megawatt and the motor load, then we have to consider another 20% margin. This 20% margin either we can put over the entire transformer or we can calculate only on the 2.50. So I have considered in the overall transformer with a 20% margin. At the final size it is coming 5 on 2 MVA trans 5 or simply 5 MVA transformer required to cater for the normal load with a normal during running condition with a 20% future margin. But with this capacity, I don't know whether motor will be starting or not. To calculate the motor starting kVA requirement, we have calculated with the motor starting kVA requirement. In that case, kVA 909, base load is equal to how much? 92500. So total coming how much? Kilowatt is coming 3409. Okay, 3409 is the starting during starting of the motor. Kilowatt requirement is 3409. Light down over here. So during starting, our total power requirement P1 is equal to 3409. And how much starting kVA requirement? That is equal to, we have got the base load is 1529 plus starting required 3136 divided 1.5 is coming 2100, you can say roughly. So this is coming equal to how much? If you calculate sum of these two, this is coming actually 3410 kVAr. This is the required during starting. This amount kilowatt is required, this amount of kVAr required. So what is the kVA requirement? kVA requirement, we can, here we are not considering SPR now. So kVA equal to how much? That equal to a square root of this 3.4 square in megawatt I am calculating, and this is a 3.4 square. If we calculate this thing, it is coming approximately 4.97 MVA is a capacity requirement. And if we put another 20% margin on the during starting, we need not to consider the 20% margin on the entire. Only we will put on the base load. That base kV how much? 250. Base kV is a 2941. That means you can say 3 MV is the base load, continuous load. Over that we put 20% margin, means is approximately 1 MVA. If we add another 1 MVA as a SPR for future, then it is coming 5.97 MVA. So that you can consider 6 MVA transformer. So for starting the motor with the 20% margin on the base load only, we need 6 MVA. And if we want to run the motor with this base load, during running we need about 5 MVA transformers. Out of this is a higher size, so we have to go for 6 MVA transformer. So that is if we go for the oil natural ON AN, oil natural air natural. Okay. So now we have to go for back to the calculation for the voltage drop. Now if this transformer is a Z% impedance, so we can calculate the voltage drop. Voltage drop how much? We have already said percentage voltage drop. How we can calculate? Percentage voltage drop that equal to S starting kVA by short circuit kVA. So S starting kVA, we know S starting kVA how much? We have got the starting kVA of the motor, percentage volt how much? S starting kVA we have calculated. S starting kVA here, S starting kVA of the motor is how much? 3410 S starting kVA. So 3410 S starting kVA. This divided by transformer is 6 MVA, 6 into Z. This will be the voltage drop. So if you calculate this thing, it will be coming about 1 point how much? This will be coming very less. This will be voltage drop. So 3410 divided 6000. So this is coming 0.56. 0.56. So this 5% voltage drop 0.56 Z. So if we consider Z 8%, so it is coming about 4% voltage drop additional. So that is all right because we have said up to 5% additional voltage drop we allow. So voltage drop is also, even it is 8%, if you go 10%, about more nearly 10% percentage impedance, this will be working. So this way we can calculate the transformer sizing. Now here we can optimize the transformer size because though we are taking the 6 MVA transformer, actually we will be using only about 4 MVA, balance 4.1 MVA, and balance power will be remain ideal always. Okay? Even with the 20%, when the 20% future load will coming, it will be coming only 5 MVA. Still 1 MVA power will be running, kept spare for the motor starting. So what we can do in that case, instead of ONN transformer, we can take ONN plus AF air force with the fan mounting on this. Because when I put the fan mounting transformer, oil natural air force transformer, the transformer cooling will be ONN, normally ONAF. Okay. Normally the transformer running will be oil natural, air natural with the normal running. During starting of the motor, we will put on the fan, all the fan will be running. By that process, we can increase power by 20%. So that means if we instead of 6 MVA transformer, if we purchase 5 MVA transformer, and it will be running on normal 4.1 MVA power, so some 900 kVA power will be spare by, and during starting of the motor, as we need 6 MVA power, so what we will do at that time, we will switch on all the fan, then this 5 MVA transformer will be converted to 6 MVA transformer. So then it can cater the motor starting also. So in this case, in that way, we can optimize the transformer sizing. Okay. So this is another way we can do this. So this is about this combined transformer sizing. Now with this, we will mention another small point about the network transformer. Suppose main incoming transformer or the network transformer. We have already done a network before. We have seen that this is a generating station from where power is coming, generating transformer. Then it is coming to a switchyard. From here, we are giving a distribution transformer is going to plant various loads. Means there is a plant distribution transformer here, all these things. Okay. So now this transformer, main transformer sizing. In this way, we will do the same way. All these loads, each feeder, we calculate the load on each feeder. And how we will do this thing? We do the repetition of the same like our distribution transformer. We calculate, this is a feeder, each feeder load we calculate. Then each feeder, how much connected load we will calculate. And with this load, we have to calculate how much maximum demand on each feeder. If the feeder has a connected load, suppose this feeder connected load is a 4 megawatt. And actual running is maximum running at one time 3 megawatt. So that means this load has a 3 megawatt maximum demand. In this way, each feeder maximum demand will calculate. Then using diversity factor of suppose 1.25, we can calculate the total maximum load coming on this transformer. Over that load, we can put another 10% margin, not 20% margin. 10% margin will give the transformer capacity of this main incoming transformer. So main incoming transformer sizing will be decided the same way as we made for the distribution transformer for the plant. We will find out each feeder connected load. From that, using demand factor, we will calculate the maximum demand. Each feeder maximum demand sum of, using diversity factor, we will calculate the maximum demand coming on the main incoming transformer. With that 10% margin we can get this transformer sizing. For the generator transformer sizing, it will be like the same as the generator cover. If this generator is a 500 megawatt generator, so in that case, this transformer will be single phase 3 number transformer. So each transformer will be 500 by 3. That will be the capacity, or it is suppose 300 megawatt generator. So 100 megawatt 3 single phase unit will be connected, and with some 5% margin we have to calculate. But this transformer this flux density to be designed very low point of the knee point, because there is a chance of saturation. So knee point voltage of this will be very lower point of the saturation point for the generating transformer. And in this case, generating transformer, generally we do not need to put any spare capacity, but if somebody want to put some spare capacity, you can put for 5% or 10% spare capacity, because this is a huge size of generator transformer. So, but normally this type of transformer, spare capacity is not very mandatory. So normally 5 to 10% spare capacity, and this capacity will be decided based on the transformer generator capacity. This generator transformer capacity will be decided based on the generator capacity. But this network transformer or the distribution after this, when it's coming to the substation, this transformer will be same size of this one, because this whatever the power is coming over here, that power to be transferred over here. So this size and this size will be identical. So main network transformer sizing will be decided based on the main generating station, how much power you need to cater. Based on that, it should be decided. Main plant incoming transformer will be decided, size will be decided, same way as distribution transformer as we discussed in session 2, same way you will decide, but the margin we can keep only 10%, as this is a quite big size of transformer. So this is all about transformer sizing, but one of the things we have to keep in mind that during transformer sizing, temperature rise point is to be kept in mind. We should not increase the temperature rise above the limit point. And second point is that before overloading of the transformer, we have to take the previous record of the transformer, what is the previous load before loading. So based on that, we have to decide the overloading factor. But at the end, it is recommended to avoid the overloading of the transformer as far as practicable, because overloading of the transformer will deteriorate the insulation, it will reduce the life of the transformer. That's why overloading, frequent overloading should be always avoided, and continuous overloading of the transformer shall not be done at any time. Only temporary overloading during motor starting could be done, considering taking the history of the transformer, then only overloading will be done. So this is all about transformer sizing. Friends, if you have any question, you can put to my email. I'll try to answer to all of you. Thank you very much indeed.